15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Hello once again. Thanks for joining us. This is the Space Nuts podcast. My name's Andrew Dunkley, and joining me as always is the good professor, astronomer at large, Fred Watson. Hello, Fred.
Hi, Andrew. How are you doing? Good to see you.
Well, yeah, good to see you too. Unusual this week because I'm actually in Sydney and I'm recording from my hotel room this morning. We've got a family member in hospital, so we've had to rush down for a visit and to sort quite a bit of personal stuff out, which I won't go into, but it's been a pretty hectic couple of days, I must say. But the good news is she's doing well, and we'll have her home tomorrow to recuperate. So that's the plus side of the ledger. But it was a pretty nasty week, to be honest. But yeah, these things happen in life, and you just got to grit your teeth and get on with it, which is what we've done and what she's done. And yeah, she's a real trooper, and I'm very proud of her. And yeah, we're hoping for a speedy recovery. How are you, Fred?
Fingers crossed. Yeah.
Yes, fingers crossed indeed.
Yeah.
Now, you're good? You're all good?
All good to go, yeah.
Yeah, all right. Well, let's get down to business because we have got a lot to cover. There are a few stories that have hit the headlines this week. One has got to do with the Parkes Radio Telescope, which we affectionately call the Dish, and they do giant salads in it. But when they're not doing that, they're looking at the stars. But it's in the news this week for a completely different reason, which we'll tell you shortly. We'll also be looking at the Galah Project because they've released data on hundreds of thousands of stars, which will be rather fascinating to go through. And we're going to do each and every star one at a time today. We'll also be looking at this really exciting story, I think, Fred, of an extra planet that existed in our solar system. Now, we've talked about Planet 9, and there's still kind of division over whether or not it exists or existed. One wonders if this might be the elusive Planet 9. I suspect not, because I think this planet got kicked out of the solar system a long, long time ago. But we'll look at that. And we've got questions. One fascinating question from Adam about Jupiter becoming a star. Let's hope not. And questions about orbiting mechanics from Paul. So we'll tackle all of those things today, Fred. But first to the CSIRO and the Parkes Radio Telescope, which has been given a new name.
Indeed, that's right. Its formal name is the CSIRO Parkes Radio Telescope. CSIRO, of course, the Commonwealth Science and Industry Research Organisation. The Parkes Dish, 50 years old now. In fact, it's more than that, actually.
Yeah, it would be.
Nearly 60 years old. It's 1961 was when it was built.
I hate to think of a radio telescope not being as old as me, so let's just keep it at 60.
There aren't many telescopes that are as old as me, Andrew, I can tell you. But what has happened is something really very nice. And I should preface this by mentioning that here in Australia, we are in the middle of something called NAIDOC Week.
Yes.
And NAIDOC is an acronym, in fact, which stands for National Aborigines and Islanders Day Observance Committee. And it goes back many, many years, actually. I think the first event was back in 1975. So it recognises the traditional owners of Australia. And that is an extremely important thing, which we are all very keen to do. And what has happened with the Dish, the Parkes Radio Telescope, is that the operators thought that it would be very appropriate for it to have a name in the local Aboriginal language, which is actually Wiradjuri. Wiradjuri is it's both a language group, but of course an area as well, and indeed a people. It's a tribe in a sense.
Exactly right. Yes, I think just to sort of fill in that blank, the Aboriginal people before white settlement lived in tribal regions, if you like. Yes. They had states or provinces, whatever you want to call it. Wiradjuri was one of the biggest ones.
Indeed,
it's a massive region, and so where I live normally in Dubbo is Wiradjuri territory. And they all had their own unique languages and words for things, and those words are translated today. And many of the streets, I think I've mentioned before, many of the streets in Dubbo are of the Wiradjuri language, and even many of our street signs have been redesigned with Wiradjuri design. So it's really quite unique, and it's a lovely tribute. So yes, and good to have the dish given one of these localised names.
Which I think is perfect. It's a lovely name. It is Murray Yang. And Murray Yang in Wiradjuri, in the Wiradjuri culture, is the home of Biami. And Biami is the creator spirit, and his home is in the stars. And so here's this telescope that has spent its entire career looking upwards at the stars, being named after that very, very appropriate name, Murray Yang.
Yes.
It makes me think, Andrew, so not very far from where you live, from the Wiradjuri country in which you live, across the sort of border into the Gomeroi country, which used to be Kamilaroi but is now Gomeroi. Is where the Siding Spring Observatory is, the Siding Spring Telescope, which I used to be astronomer in charge of. And I've got friends among the elders there, in particular Auntie Maureen Salter, who's a very well-known person within the Coonabarabran area, which is the nearest big town. And I wondered whether we should be talking to her about renaming the Anglo-Australian Telescope, something a little bit more in keeping with the Gomeroi tradition. The mountain itself is called Siding Spring, but it also has an Aboriginal name, which is Woorat. And so there's a start. We maybe should have the Woorat Observatory, Mount Woorat Observatory, rather than the Siding Spring Observatory.
Got a ring to it. Sounds good.
It's got a ring, hasn't it?
Yeah.
Anyway, a short story, but one that I think, is well worth celebrating. So Murray Yang, the new name for the Parkes radio dish.
Wonderful. Wonderful indeed. Now, Fred, let's move on to the next story straight up. And this is a project that I know you're very, very knowledgeable about, the Galah Project. And they have released chemical information for well over 500,000 stars, closer to 600,000 stars. So let's start with star number one.
Okay.
Or maybe,
the first one is...
maybe just do a collective overview of what they've found out. That might be quicker.
That might be quicker. That's right. So, and actually this segues very nicely from what we've just been saying about the Anglo-Australian Telescope, which is at Siding Spring Observatory. This is a project on the Anglo-Australian Telescope, and that's why I was involved with it. So Galah is, first of all, it's an Australian bird. You and I have spoken about this before.
Oh, yeah.
On Space Nuts. It's an Australian bird with...
noisy darn things too.
Attractive bird, very noisy. But in this case, it's an acronym, and the acronym Galah stands for Galactic Archaeology with Hermes, because, of course, Galah is spelled G-A-L-A-H. So Galactic Archaeology with Hermes, that folds another acronym into it, because Hermes is an acronym for the big spectrograph that we have at the Anglo-Australian Telescope. I won't bother with what that is. I think high efficiency is where the HE comes from. And resolution, I think, is the R, multi-object, multi-something spectrograph. There you go.
And for people who are wondering what a Galah actually looks like, they are pink, believe it or not.
They are.
And
Beautiful.
I think I've got a photo of one there. There you go. Pink and grey Galahs, native to this part of the room.
I can't see the picture here. There you go. Perfect.
They're
yes.
very, very pretty.
Did you drag that? Oh,
we get them in our front yard, Fred, and all over the golf course. They are quite
many
scrawchy little creatures. They love to make a bit of noise. Yeah. Just thought people might like to see one.
You must know the recipe for cooking a Galah as well.
Yeah, now I've heard this. It's the same as cooking rocks, isn't it?
It is. That's
boil
right.
them. So boil them, and
you boil it up with a rock. You put a rock and a Galah in a bucket, you boil them for 10 days, and you throw away the galah and eat the rock.
I knew it was something like that. I love it.
That's a good one. Anyway, the Galah survey is different. This uses this instrument, Hermes on the telescope, allows you to observe up to 400 objects simultaneously. So it's a great way of collecting information on large numbers of stars or galaxies or indeed quasars. And that's what the telescope has done with that kind of equipment for many years. Hermes is relatively new. It was commissioned, if I remember rightly, at the end of 2014. And so the project, the Galah Project, is to do galactic archaeology, as I said in the intro there. And galactic archaeology is the study of the kind of the entrails of our galaxy. How did it get to be like it is? What other galaxies has it absorbed in its 12 or 13 billion year history to become the large galaxy that we see ourselves surrounded by here in the plane of the Milky Way? And Galah does this in an interesting way. So you might remember you and I have spoken about the RAVE project before, which I was project manager for. It's on another telescope at Siding Spring. And that was principally concerned with looking at the speeds of stars. And from that, you can actually find out about the way our galaxy has grown, because of some stars have speeds or movements which are related to the original galaxy that they came from and that was swallowed up by our own. Hermes does the same thing, but from the chemical point of view. So it's looking at the chemistry of the stars. And from that, we can see, for example, that 8 billion years ago, there was a big collision event involving our galaxy, which means that there are different species of stars, if I can put it that way, stars with different chemical histories within our own galaxy. And Hermes is able to tease those out. So that's one of the big discoveries that comes from this new catalogue of 600,000 stars. The reason why we're talking about this is that when you do a big survey like this, what happens is you release the information as it's collected and analysed, and these things are called DRs, data releases. So DR3 has just been published. It's got something like 50 authors, I think. I'm not one of them. I actually didn't put my hand up for it because I haven't really done any observing for Galah for about the last 2 years. So I didn't feel it was appropriate for me to do that. Although I think I'm an author on many of the other Galah papers, including DR2, the second data release, which was back in 2018. So DR3, the third data release, 600,000 stars with all these intimate details of each star, including the velocity, but also these fine details about the chemistry and things like the surface temperature and surface gravity, the effective temperature, surface gravity. All of these are parameters that come out of it as well. So a major new catalogue, which other astronomers can now address and can extract information from it to make their own deductions about the history of our galaxy and look at what has led to this magnificent spiral galaxy that includes about 400 billion stars, including one called the Sun.
Oh, wow. I'm glad we know something more about that one. Pretty handy.
That's in there.
Yeah, but you might have already said this, but it's almost, it's around half a terabyte of data.
Yeah, that's right. It's a colossal amount of data.
Yeah, incredible.
Indeed.
Yeah, and I read one thing that they were talking about, and that is lithium, one of the elements created during the Big Bang, and they're talking about how it gets destroyed by some types of stars. We would be in deep peril without lithium because we use it to store power and run cars and phones and so many other things. It's one of the most
used in medication as well.
Yeah, one of the most necessary elements that we have on the planet at the moment, amongst many. But without it, we'd be toast.
That's right. There is something well known in galactic archaeology called the lithium problem, because we can't. Lithium is one of the elements that was created in the Big Bang, one of the few elements that actually was generated in very small amounts, but it was created in the Big Bang. But we sort of can't tie up what we see today in the spectrum of stars with what was produced in the Big Bang. So actually, Sanjeev Sharma, who's one of the authors of this paper, somebody I know pretty well, he's a great guy, a young researcher who does wonderful things. He says about this problem, he said, basically, a lot of the oldest stars have burned much of the Big Bang lithium. So our measurements for this element come out lower than the amount that was initially synthesized in the early universe. At the same time, we found that one type of star, known as evolved giants, should have burned through pretty much all of their lithium by now, but a lot of them has much more of it than we expected. And the Galah data will help us discover why. So the lithium problem is an ongoing one. We really don't know the full details of the history of the lithium that was created in the Big Bang.
The other lithium problem is domestic, and what we are going to do to power our devices when we run out of the stuff, because there ain't that much of it.
No, there ain't. That's right. Got to go and mine asteroids, Andrew.
Well, maybe that's what it'll come down to. Who knows? But I'm not sure. I'm pretty sure we'll run out before we have the technology to do that, I suspect. But is there any on the moon?
Not much, no, but there are, as far as things like battery technology is concerned, there are alternatives now using sodium and things like that.
Well, there's plenty of that around.
That's right.
Okay, very good. You're listening to the Space Nuts podcast. You're also viewing the Space Nuts vodcast on YouTube. And my name's Andrew Dunkley, of course. With me is Professor Fred Watson. He's over there. Or is he over there? I don't know which one.
No, he's over here.
We'll be back shortly.
Roger, you're loud and clear here also.
Space Nuts.
Thanks for joining us. This is the Space Nuts podcast and the Space Nuts vodcast. I don't know what we're supposed to call it, but we'll stick with that for the moment. We'll just call it Space Nuts. Thanks for joining us. Andrew Dunkley here with the good Professor Fred Watson. Now, we're going to look at a planet now. This is a planet that may still exist, may not exist. It might have been smashed up in the Kuiper Belt. It used to exist in our solar system in the early years, they think, but it got kicked out because that's what happens when planets are naughty. Like me at school, I got sent behind. I'll tell you this story. When I was in primary school, Fred, I was naughty, and I got sent to behind the door. That's where they used to send the naughty corner. So I got sent behind the door, and I was there for quite a while. And the teacher said, "Are you ready to come out yet?" I said, "No, I don't think so." She said, "All right." So I stayed there. I don't know what I was thinking. I was embarrassed. I didn't want to come out. Anyway, and that's possibly what happened to this planet.
Are you ready to come out yet? No.
No.
Yeah.
And it's still hiding.
So, still hiding, that's right. So what's the story about? It's work that's come from the Carnegie Institution, and it's all about studies of our solar system and looking at the dynamical history of the solar system. We've just been talking about the history of our galaxy. Well, you can do the same thing on a much, much smaller scale in looking at the way our solar system has been built and how it has evolved over its 4.6 billion year history. The interesting thing about the solar system is it seems to be quite different from the other solar systems that we're now able to study, because we can analyze the planets of other stars. Something well over 4,000 planets now known orbiting other stars, and many of them are in multi-planet systems. So it gives us a chance to get at least a snapshot of what solar systems generally are like. They're not like ours. No. Ours is a little bit unusual because we've got these 4 rocky planets close to the sun and then 4 giant planets further out. And the thinking is that there has been migration of the planets they over the full history of the solar system. While their orbits are extremely stable now, over the full history of the solar system, they may have changed. And so in analyzing this, a team of researchers basically looked at what the current layout of the solar system is telling us about its history. And actually, one of the team that has done this, in fact, I think he's the lead author of the paper about it, somebody called Matt Clement. He's a postdoctoral fellow at Carnegie Institution. He says, we we now know, this is what I've just said, that there are thousands of planetary systems in our Milky Way galaxy alone. But it turns out that the arrangement of planets in our own solar system is highly unusual. So we're using models to reverse engineer and replicate its formative processes. This is a bit like trying to figure out what happened in a car crash after the fact, how fast the cars were going, in what directions, and so on. So it's really nicely, sort of kind of reverse engineering of in a forensic way. That's what I was looking for, like a forensic analysis. And they've done 6,000 computer simulations. And what they've found is that the final arrangement, if you like, the way the two ice giants, Uranus and Neptune, are positioned within the solar system, that was determined by two things. One is the mass of the Kuiper belt. That's the icy asteroids which are beyond the orbit of Neptune, in the far reaches of the solar system. But you also need, in order to get this arrangement between Uranus and Neptune as we see it today, you need to have had another object in that region, probably between them, an ejected ice giant, kicked out when the planetary system was still young. And actually, Matt Clement's comment about this is that this indicates that while our solar system is a bit of an oddball, it wasn't always the case. And that then allows them to look at the formation of the terrestrial planets and see what might have happened to them. So the thinking is that very early in the history of the solar system, maybe within the first 500 million years or so, like 10% of its present age, there was a similar planet to Uranus and Neptune, an ice giant, that due to gravitational interactions between those two, and probably planets like Jupiter as well, it was thrown out of the solar system. In other words, it was given a gravitational boost that put its velocity up to greater than the escape velocity of the solar system. And so off it goes. Our chances of finding it today are approximately zero, because it probably is one of these rogue planets now that you and I have talked about before.
Out there floating around somewhere, possibly in a galaxy far, far away.
It's almost certainly not in a galaxy far, far away, but it may be in a solar system far, far away, because it will definitely still be in our own galaxy. Just, you're never going to kick it out of the, it's very unlikely that you would put enough velocity into it to kick it out of the velocity, out of our galaxy. So the escape velocity in our solar system is in the region of 20 to 30 kilometers per second. The escape velocity for the galaxy is in the region of 200 to 300 kilometers per second. So that's why it's probably still in our galaxy.
But where it went, we know not.
Don't know. That's right. Yeah.
It probably didn't like its brothers and sisters and has divorced the family. That's what happened.
So it could have dumped the family. That's right. Or it could have been, as you said, sent to the naughty corner, which is a place rapidly receding into the distance.
And the teacher will never ask if you want to come out. So that's that.
No.
That's the end of that.
You've got one chance on it. That's it.
Have we ever found one of these sort of rogue planets?
Yeah. There are many known, actually. A whole cluster of them in the constellation of Orion, which seem to be associated with the Orion Nebula. They, I think, were the first found. This is probably 30 years ago now. But they are identified. They're identified. You might wonder how you find a planet that doesn't have a star to light it up. And it's because many planets, including the Earth, have got internal surface sources of heat, which are caused by residual nuclear reactions left over from the formation of the planet. There was a lot of uranium in there, which is fissile material. So that generates heat, and that heat is able to be detected with very sensitive infrared telescopes. So that's how we find them. We're finding exoplanets, we're finding rogue planets. We obviously know about the planets of our own solar system. Are there any other kinds of planets that we don't know about? It's all a matter of scale, actually. And we should probably postpone this discussion, because one of the questions that we've got coming up...
Good point. Yes, that might have been what seeded the thought in my mind.
What seed in
My
the
brain
thought?
does weird things sometimes.
Yeah.
All right. Well, we'll get onto that very, very soon. You're listening to the Space Nuts podcast. Andrew Dunkley here with Professor Fred Watson.
Space Nuts.
Now, I'd like to thank all our patrons, the people who put their money where our podcast is. And it can be as little as a few dollars a month to as much as you like. But as I mentioned last week, we have a new process where you can buy 12 months in advance and get 2 months free, which is a fabulous deal. And we've got a few people who've signed up for that already. In fact, they signed up before I knew it existed. But that's fantastic. We are so thankful that you're willing to part with a few dollars to support our podcast, because it was something that the audience came to us with as an idea. We never originally pursued. We didn't even know about it until someone said, how do I support the podcast financially? And we looked into it and we found a few options. So there's Patreon, there's Supercast, there's Acast, or you can just make a one-off donation via our website through Acast. So all the details about becoming a patron are at our website, spacenutspodcast.com. And, of course, as a patron, you get bonus material, you get the ad-free version of the podcast, and you get it early, except at times like this when I've had to travel to Sydney and I'm recording at the last minute. So we could have almost done it live, but maybe one day we will. But thank you again to our patrons. Your support is generously and most gratefully received. Now, Fred, let's move on to our question segment. And we are going to start off with a question from Adam, who is in Hastings, Victoria. Hi, guys. Love the show. You're the first person who said that. I've been observing Jupiter through my telescope quite a lot recently and can't get enough of it. I remember a comment that Jupiter is so massive it could possibly be considered a star which failed to ignite. I may be imagining that bit. This got me to wondering what would be the effect to Earth if, in fact, Jupiter did ignite. It is a fantastic question, and I can't wait to hear what you've got to say about it, Fred.
Well, look, turning to the last bit first, yeah, it will be curtains for us. If
I kind of figured that might be the case.
Yeah, I think it would change the dynamics and the radiation field, if you like, of the solar system so much that it's very unlikely that we'd survive. So that's all right. It's not going to happen.
So nobody take matches when we're going to nobody. Matches are not on.
No, that's right. Forget it. Yeah. Watch where you're throwing your cigarette butts as well.
And knowing humans as I do.
Yeah, exactly. So the bottom line is, yes, it is a commonly heard comment that Jupiter is so massive that you could consider it a fail, not so much a star that failed to ignite as a failed star, because it's not massive enough to be a star. So as the solar system evolved in its very early infancy, so what you've got is a gas cloud collapsing to become a star and the dusty debris accreting to form the solar system of planets. That's all, good stuff. And we all believe that all happened. What if, in fact, Jupiter had accreted more gas, more of the hydrogen gas than it did, and got to the level where it could ignite? What you would have would be a binary star system with probably a very different distribution of planets. But that didn't happen. So it never accreted enough gas to become, the process is that you get so much mass of gas that its own gravitational pull compresses it, and eventually it's compressed to a temperature at which nuclear fusion starts. That's how the sun switched on. And the same would have happened if Jupiter had become big enough, but it didn't. And it ran out of gas to accrete at a stage where it's not enough for nuclear processes of that kind to take place. Although, and I'm pulling the figure out of my head here, Jupiter does have nuclear processes going on inside it, low-level processes, which we've just been talking about in regard to rogue planets. And if I remember rightly, it emits something like, I think it's 1.5 times more radiation than it receives from the sun. So, and that is stuff that's coming from these nuclear processes inside.
Okay.
Now, if it had got a bit bigger, it would have turned into a kind of star, and it wouldn't have had to get that much bigger, because once you get to 13 times the mass of Jupiter, an object is defined as a brown dwarf star. And so this is really a failed star, in the sense that it's not big enough for nuclear fusion to take place. But there is something called deuterium burning, a nuclear process that actually makes it glow in the infrared more than Jupiter glows. So 13 Jupiter masses is the trigger point for a brown dwarf. And I think the upper limit is something in the region of, if I remember rightly, 60 to 100 Jupiter masses. Once again, I'm pulling figures out of memories from a long time ago, because once you get to that stage, then it will start burning. It will start burning hydrogen. It'll become a genuine star. So a deuterium burner is a brown dwarf, and just low-level fissile processes like what are going on in Jupiter, that's a planet. Yeah. And that's what we were just talking about a few minutes ago. So it won't ignite. It might have done had it collected more hydrogen 4.6 billion years ago, but it didn't, so we're okay.
So we should assure Adam that it won't ignite. It can't ignite. It's just not possible in the future. Exactly. I mean, what would it take for it to reach that point? It would have to merge with something massive, wouldn't it?
Yeah, it needs more. The hydrogen fuel that went into the sun is all gone into the sun, rather than and so stars are born in nebulae, which are very rich in hydrogen. That nebula that the solar system was born in has long since been cleared away by the radiation pressure of the stars that were born in it. So the sun has siblings somewhere which were born in the same nebula. We haven't found them yet, although I think there are some candidates that have exactly the same chemical composition as the sun. Yeah,
although we did talk recently about the sun possibly once being a binary, and that there was another star a long way away that used to be part of this system. And you did say that if Jupiter did become a brown dwarf at some stage in the past, it would have been a binary system with our existing sun.
Yes, that's right.
Would it have survived, though, if it became a brown dwarf as against our existing sun, or the sun as we know it? Would it survive in a binary situation so close together?
Yeah, I think so. I think there are examples of normal stars with brown dwarf companions.
Okay. Yeah, so interesting. Yeah. All right. Many thanks for your question, Adam. It's a ripper. And we'll move on to our next one, which comes from Paul, who lives outside of Atlanta, Georgia. Hello, Andrew. Hello, Fred, long-time listener and Patreon supporter here. Have I got the right question? Yeah, I have.
You do, yeah.
Now, orbital mechanics question for you. Long duration space-based observatories like DSC OVR mission, Discover, I assume that stands for, and the upcoming James Webb Telescope take advantage of the Earth-Sun Lagrange points, L1 and L2, points of special orbital stability. Does the technology exist for launching missions to other Lagrange points like Venus, Sun L1, or Earth, Sun L4, L5? Does the motivation, extra credit question, are Earth, Sun, L4, L5 orbits stable to, I can't read the word, perturbation by Venus, such a point would be within minus 0.2, is that 0.25 AU of Venus at its closest approach? Many thanks for, as always, engaging broadcast, notwithstanding the terrible reading I just did of your question because I forgot to pre-read it. Biggest failing in my radio career.
You did a great job. So let's just step back a bit. What are these Lagrange points? They are 5 stable points. Whenever you've got an object in orbit around another one, you get these points where the gravitational force is balanced by centrifugal force, effectively. And so the points are given names. Let's just think of the Earth and the Sun. The L1 and L2 points are, one of them is between, L1 is between the Earth and the Sun. L2 is about, it's about 1.5 million kilometers, if I remember rightly, on the other side of the Earth, in line with the Earth and the Sun, but on the opposite side. L3 is on the far side of the Earth's orbit, directly opposite the Sun, and L4 and L5 are 60 degrees ahead of and behind the Earth's orbit, the Earth as it goes around in its orbit. So these are all stable points where you can place spacecraft, and they are basically stable. And so Paul's question is, can you use some of the other Lagrange points, like the ones relating to Venus rather than the ones relating to the Earth, just to summarize that. Venus Sun L1 or Earth Sun L4, L5, that's the 60 degrees ahead of and behind the Earth in its orbit. And the answer is yes, the technology is definitely there. It will be possible to place a spacecraft. In fact, you don't put it exactly in the stable point, you put it in an orbit around the stable point, which sounds bizarre. You're putting something in an orbit around nothing, but that's the way these things work. And yes, we could do that. Good question. Does the motivation exist? Probably not for L4 and L5. In fact, just thinking, look, there are a pair of spacecraft already in the Earth-Sun L4, L5 positions. And I've forgotten what they are. They are sun-observing spacecraft. I'm pretty sure, I need to check this, but I'm pretty sure that those positions are now occupied by sun-observing spacecraft. And that actually feeds directly into what the last part of Paul's question is. Would the L4, L5 points, these are the 60 degree ahead and 60 degrees behind the Earth in their orbits, are they stable to perturbation by Venus because they pass close to Venus? And the answer is no, they're not stable. And my recollection is that, and I'm sorry I can't remember the name of these spacecraft, it's only just come back into my head that there are spacecraft in these points. I think one of them is either has been or is being shut down because of exactly this, the drift of this object in its orbit because of perturbations by Venus and Mercury probably as well. So the answer is that they're not stable. You need to keep firing corrective burns on your rockets. And with this particular one, that's not happening. I need to check up on this, Andrew, because, as I said, this is just stuff I'm pulling out of my memory. But I'm pretty sure we do have spacecraft already at the Earth-Sun L4 and L5 points, which is the answer basically to Paul's question. I'll shut up now.
Fair enough. I just tried to look that up to see if I could find those spacecraft, but it's not an easy, quick search. But yeah, I mean, these Lagrange points probably exist all over the place, all over the solar system, all over the galaxy, all over the universe.
They do.
Actually, a funny thing happened the other day at the radio station. One of the guys came to me and said, where does gravity, Earth's gravity stop having an effect? And I said, the Lagrange point. He said, what's that? And I had to give that explanation that you just gave. I didn't do it quite as well, but I got a raised eyebrow response, which was, I didn't know that. So I was able to suitably answer the question, adequately answer the question, which is all we try to achieve here is adequacy here at the Space Nuts podcast.
And if I may just, I've done a quick search, and there is indeed the two stereo spacecraft, Stereo A and Stereo B, are at the L4 and L5.
Now that you mention their names, I think we have actually talked about them in the deep dark past, but I don't know why. So, and if I can direct Paul to a website, which is on Wikipedia, it's the list of objects at Lagrange points. And it'll tell you all you need to know. Fantastic. There you go, Paul. And thank you so much for your question. Really appreciate it. And as we say time and time again, keep those cards and letters coming in. You can go to our website and fill out the contact form and send your questions in that way, which lots of people like to do. Or you can click on the AMA tab and press the record button. If you've got a microphone attached to your device, whether it be a smart device or a computer, laptops have them built in, of course, or notebooks or whatever you call them these days, you can just tap on that and record your question. Don't forget to tell us who you are and where you're from. We love to know that. And we will play back your questions when I am in a position to do so. Couldn't do it here today because of the circumstances I'm in, but we do love to hear from you. We've got quite a few questions. So in the not too distant future, we will probably dedicate a whole episode to answering probably 50 or 60 questions. I imagine, Fred, that'd probably cover an episode, maybe.
Yeah,
we'll see how we go. But thanks for contributing to Space Nuts. We certainly do appreciate it. And Fred, that brings us to the end of yet another episode.
Indeed. So thank you, Andrew. It's been great talking about all this good stuff, and I look forward to seeing you next time.
Good to see you too. Fred Watson, astronomer at large, part of the team here at the Space Nuts podcast. And don't forget, if you want to watch, you can do that via our YouTube channel. Just do a search in YouTube for Space Nuts podcast, and you'll see our ugly mugs, and you'll know that we've both got heads for radio, basically. That's the way it works. Exactly. It's only taken 36 years for me to reach a camera, and everyone regrets that, including my wife. Anyway, see you soon, Fred. Thanks so much. And thank you to you, the audience, and the followers and supporters of Space Nuts. We'll catch you again next time. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast. Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com. This has been another quality podcast production from Bytes.com.